Hello and welcome. In this video, we're going to be talking about the phenomenon of ChatGPT, the broader landscape of large language models, and what this all means for the future of programming. So let's go ahead and get started. So let's start out by thinking about this smaller language model. It's only small relative to something like ChatGPT, and that's Gmail's predictive text, because this is something you're probably familiar with. You may have seen it on Gmail or maybe on your phone when you start typing a text and the phone makes some suggestions about what you're likely to type next. So here's a little demo video of Gmail's predictive text in action. So we have the user typing an email to their friends Ivan and Malika. Okay. And let's just pause over here and see what happens. So as the person types haven't and then the letter S, the autocomplete fills it in with seen you in a while. So let's try to understand what is going on in this type of scenario. Okay. So the language model has basically learned to identify statistical patterns between words during a training process. And in the actual inference, when it is actually working on this Gmail screen, as you can see here, is trying to predict the next sequence of words that the user is going to write. So let's try to imagine what sort of intuitions, what sort of clues might the model have that would allow it to make this particular inference. Okay? So one thing it may be thinking in quotes, is since the user started with the word hey, then this must be an informal type of message. And therefore, it's likely to include exclamations because people tend to include exclamations when they're sending informal messages. So it puts this exclamation point there. Okay. And it may tend to include abbreviations as well. So the further completions you'll see end up having lots of abbreviations. Another thing the model may be thinking is since this person is making dinner plans, so they have dinner next week in their title, then they're likely to mention how much they miss the people that they're about to see. And this message here, haven't seen you in a while, is a way of expressing the sense of missing a person. Okay? Or it may be something just as simple as whenever people write the phrase haven't seen, they tend to complete it with you in a while. But of course, we don't really know what the model is thinking. All we know is that the model identifies certain statistical patterns between words and between phrases in the past emails that have been sent, and it's using that for this prediction. What we're trying to do here is try to guess what sort of things, what sort of correlations the model may have in mind while it is doing these predictions. So hopefully this gives you a broad idea of how statistical patterns between words and phrases can actually lead to reasonable predictions for the next words in a sequence. So given that context of a language model like the one that is used in Gmail's predictive text, let's look at a simple schematic of what a language model is actually doing. So a language model basically takes in some kind of text input. In our example, let's say the phrase haven't seen you in, and based on some corpus of text that the model has processed during its training phase, tries to predict a reasonable completion for that text input. In this case, the reasonable prediction would just be the word A. And so the model can then repeat this process, now taking in the input haven't seen you in A, and trying to, again, based on this corpus of text that it has processed, predict a reasonable completion for that. And it may come up with the word while as the text output. And so this process can be repeated indefinitely in order to create arbitrarily long sequences of words, or if you like, tokens. So now that we have the intuition for how the model works during inference, let's think about how the model is actually trained. So the training process for language models actually looks quite similar to the inference process. So here's how a model typically is trained. You give it some text input with a known but a masked completion. So some sentence or longer sequence where you know how it ends. Take this example here, a poem. Jack and Jill went up the dash. So we know that this ends in the word hill, but we give it to the model in a masked version or in a masked form. So the model can't see that final word. And the model then has to guess the completion to this sequence, and it's going to learn either from its mistake or from its success. So imagine that the model comes up with the prediction, Jack and Jill went up the laugh, which is not correct. Then the model will get penalized. But if the model happens to make a correct prediction, that is the word hill, then the model will be positively reinforced. And so the process that led to it creating this prediction of hill will be positively reinforced. Now, for those of you who are interested in the details, the model isn't actually creating a single prediction. It is rather making a probability distribution of predictions across a number of tokens. But to get a general intuition, this suffices to think about it. And so this penalization or reinforcement process then feeds back into the model's internal weights to make it more or less likely to give the correct or wrong answer, respectively. And so in this case, the model may learn some principles or some heuristics like this. In general, after the word the, you should tend to put a noun and not a verb. That could be something that the model learns. Or the model may learn something like this. If it is in a poem, and we know this is a poem, then try to find a word that rhymes with some previous words in the poem. In this case, hill rhyming with Jill, whereas laugh doesn't rhyme with anything else. Okay. And it will use these heuristics for future predictions. And if you repeat this process many, many billions and trillions of times, the model gradually gets better at making these next word predictions. So we could schematize the process of training a language model into three key components. The first is we need some training data, some information to learn from. Some large corpus of text from which we can take these known but masked completions. In the case of Gmail's predictive text, this is probably just past emails that people have sent. Okay. We need some kind of learning algorithm, some strategy with which we can update the weights of the model based on these positive and negative reinforcements that we get from the model training process. And of course, we need some computer processors in which to run this learning process because it's quite compute heavy, as we will see soon. So that's the basic process of training a language model. But now you may ask a question, which is, how do we go from something this simple, some process this simple, to something as powerful as a ChatGPT? And there are really two main answers to that question. The first is scale, the power of scale, which we'll see in a second. And the second is a little bit of instruction tuning. So let's think first about scale. It turns out that these two components, the training data and the computer processors, can be scaled arbitrarily large, and language models tend to get better as you increase the amount of training data and the amount of compute that you throw at this learning process. Let's think first about the training data for something like ChatGPT. Here I'll be talking about the training data for GPT-3, which is the predecessor to GPT-4. GPT-4 is currently one of the best models, or probably the best model out there at the moment. But OpenAI did not release information about how it was trained. So we'll be looking at GPT-3, which is a bit of a smaller model than GPT-4. So GPT-3 was trained on about 570 gigabytes of text. And where did this text come from? For one, it came from Wikipedia. So I think all of Wikipedia was included in the training data for GPT-3. Almost all the open source code on GitHub, which is millions and millions of repositories. The dataset Common Crawl, which is basically information crawled from basically all the publicly accessible websites on the internet. So some subset of Common Crawl was used for training GPT-3 and many other things. To give you a sense of the scale of this data, if you took the data GPT-3 was trained on, you printed it on a copy paper, A4 paper, and you stacked it one on top of the other, these sheets of paper, you would get about 56 Eiffel Towers. So just to give you a sense of the scale here of what we're talking about in terms of the training data. Now, a small thing to clarify is that in the process of training a model like a GPT-3, the model was actually making predictions based on the previous about 1,500 words. So in the examples I've given you, like the Jack and Jill example, the model is trying to predict based on very few words, maybe 4 or 5 words. But in reality, when you're training these big models, you need much more context. And so the model usually gets about 1,500 words of context. So that's a bit about the training data for GPT-3. So let's think now about the processing power, the compute that was used to train this model. So lots and lots of parallelizable GPUs are required for training modern language models. In the case of GPT-3, one estimate is that you would need about 100 NVIDIA A100 GPUs, and each of these GPUs are fairly large, and each of them costs about $10,000 US. Okay? And you need to run them for 1 year. So 100 of these 10,000 US dollar GPUs all running together for 1 year, repeating this training process. So it turns out that if you take that simple process of training the model on next word prediction and you scale it to very large amounts of data and very large amounts of compute, you get out these things that seem quite intelligent. There is one more thing, though, that makes ChatGPT as helpful as it is, and that is instruction tuning. So let's think about what instruction tuning is. So instruction tuning helps us go from what are called the base models to these instruction tuned models, or you might sometimes hear them called instruction fine-tuned models. Instruction tuning is basically the process of training the model towards a helpful and correct responses. So let's think of an example. Imagine that you gave a model the following text input. What is the capital of Australia? A naive model, a non-helpful model, a non-instruction tuned model may just give you an output like this. What is the capital of New Zealand? That is what it predicts will be the next most likely thing to come after the sentence, what is the capital of Australia? Why is this the case? Well, in many instances where the model during its training encountered sentences like this, what is the capital of Australia? Many of those may have been lists of trivia questions or lists of quiz questions where the answer doesn't come right after the question. So this may actually be a likely completion for this text in the corpus of training data. Just long lists and lists of questions. So while this is a reasonable guess for the next most likely thing to be typed, it isn't a particularly helpful response. Okay. Another thing that the model may give you is it may say the capital of Australia is Sydney. Why might it say this? Because again, it's just learning from internet data. And on the internet, many people are wrong and think that Sydney is the capital of Australia. And so this completion, while being reasonable, if all you're trying to do is predict what might come next in this text that you see on the internet, is not particularly correct. Well, it's exactly not correct. The correct answer, of course, is Canberra. And there are many places on the internet where this is stated, that the capital of Australia is Canberra. Okay? And so what instruction tuning consists in doing is giving the model many questions like this or many inputs like this and rating the correct and helpful responses as correct and helpful. That is reinforcing the model positively when it gives these types of responses and negatively when it gives either these unhelpful ones or these incorrect ones. And so this process helps steer the model towards some notion of helpfulness and correctness. So to summarize, it turns out that training a model on this simple next word prediction task, but scaled on lots and lots of data and lots of compute, and then instruction tuning that model gives you a seemingly intelligent and extremely helpful assistant like ChatGPT. And for those of you who are not yet sold on the usefulness and the intelligence of these large language models, I'll do a live demo of GPT-4, which is currently the state-of-the-art or the best-in-class model out there. Okay, so here's the demo I'm going to do. I'm going to give GPT-4 the following task. So I say, consider the following dataset that I have in R, whose first 10 rows are shown. And I show the first 10 rows of the dataset here. This is the dataset from the movie Star Wars, and each row is a particular character in Star Wars, and you have information about these characters, their name, their sex, their height, their species, and so on. And I'm going to ask the model to make a plot that shows whether human or non-human species tend to be taller. As you can see in the species column, you have some humans and then a bunch of non-human species. Okay. Then I'm asking the model to write the title and subtitle in French and to add a caption to the plot with a poem, an English poem, about whether there's other intelligent life in the universe, as the Star Wars movies suggest. So if the model can give me a reasonable completion of this task, it will be exhibiting coding proficiency, multilinguality because we have the French and the English in there, poetic ability because I asked it to write a poem in the plot, data analysis expertise, knowing what sort of plots will make sense to illustrate what kinds of points, and responsiveness to feedback because I'm going to ask for some follow-up questions based on the result that it returns. So let's go ahead and see if GPT-4 is capable of doing this task. So now I've gone ahead and opened up my ChatGPT window and I've pasted in that question in there. All right, so let's go ahead and run this and see in live view what the model is doing for a completion. So first is creating a new variable in the dataset that will classify species as human or non-human. That's quite useful because notice that here we have the species column and we have these many alien species, and then you have this human as another value. So you're going to have to collapse all of these alien species into a single species. And that's what it's doing there with the if-else function. And overall, this looks quite correct to me. It's creating a bar chart to show the average height by species type. And it's putting in the title and the subtitle. And it's writing the poem in English. And I think that is basically ready now. So I'm going to copy that code. Okay? And I'll pull up my R console so you can see it here. And I'm going to paste that in. And let's try to run that and see what kind of plot it gives us. Okay. So what we have here now is the mean height by humans and non-human species, which is quite correct. I think this is a good visualization. However, I may be interested in looking at the distribution of heights, not just the mean height. So I'm going to ask the model, please give me a plot that shows the distribution of heights instead of the mean height. So I'll say I'd like the distribution of heights, not just the mean height. Okay. And let's see what it does now. Okay, so now we have this updated code. Let's copy that again and let's paste that one more time into our studio and take a look at the new plot. Okay, so now we have this new plot with a box plot showing the distribution of heights for the humans and non-humans. And as you can see, for the non-humans, there's a wide range of heights because these are from many species. And for the humans, the range is much smaller. And of course, you can see that the title is correctly in French. I think this is good French. My French is not that great. And let's read the poem and see if the poem makes sense. It says, in the vast expanse of space, there exists a place where humanoids and aliens from the farthest stars race. In worlds known and unknown, life does dwell. In forms strange and familiar as the Star Wars sagas tell. That is a better poem than I would have been able to write about humans and non-humans in Star Wars. So going back to our presentation, what we have demonstrated is that this model can code reasonably well. It is quite multilingual. It has decent poetic abilities. It can do data analysis, and it is very responsive to feedback. What a time to be alive.